So, in the previous video on electrostatics, we had gone up to discussion about the properties of charge, where we had discussed the first property, that is, the charge is quantized, which means that it has fixed or integral values or values in integral multiple of the factor E, which is the charge of an electron or a proton. Now, in this video, we will be discussing the other properties associated with charge, as well as the case of transfer of charge from one body to another, the methods that we employ, and so on. So to begin with, we have the second property that we were to discuss, that is the case of conservation of charge. So the second property tells us that charge is conserved. What does that mean? Well, take the case of a given system comprising of a few particles. Let's say we have a system over here. I'm just assuming a segment of some space, and we have a few particles which are carrying a certain charge with them. Now, as you can see, I have just arbitrarily provided the positive and the negative signs which imply the charge carried by those objects which or particles which are present in that given enclosure that I have just drawn. Now, even if whatever may be the case, whatever may be the transfer of charge between all these particles that are present over there, the eventual result is always going to be the same. Suppose you may consider these two particles becoming one, these two particles becoming one, and you have a neutral, two neutral particles now. In the beginning, there were probably 5 particles. Now you have 3 particles with 2 being neutral. But what about the charge that is carried? Now the charge that is carried, as you can see, there is only a single excess charge that is left, that is the plus charge. Now go back to the beginning of the situation where we had 5 charges or 5 particles. And in those 5 particles, what you observed is that you had 3 positive charges and 2 negative charges. And if you go on to add them up, the positives and the negatives will get cancelled out, the pair, as they have done when they have become one, and eventually you will be having a final positively charged particle. So that means that a given space, the space can be extended right up to our entire universe. That space, when considered carrying some particles or few objects which carry certain amount of charge, the total charge is always going to remain the same till the eternity. There may be exchange of charge between particles or objects, but eventually the total charge that was considered within a given system, that is going to be the same every time. Suppose you consider 2 objects where there is a transfer of charge, probably by friction. So if you have one of those objects over here and the other object over here, and there was some interaction between them, as a result of which previously probably they were neutral and they had no excess or deficit of electron in them, and due to some interaction or the other, one of them gave away, suppose, 5 electrons to the other. So now this will carry a charge of minus 5e. We know the value of E, and this will now carry, because it has lost electron, this will carry a total charge of 5 plus 5e. But what about the case of considering the entire system which was comprising of both these bodies? The charge remained conserved for both of them, for that entire system, because initially they had 0 charge, and due to some interaction probably, so the total charge of the system was equal to 0. 0 plus 0 equals 0. No element of surprise in that. But what happens after the interaction? Well, after the interaction, one of the bodies has plus 5e and the other body has a minus 5e. But you consider the total charge of the system, that again comes out to be 0. So this is what I was trying to say, that the total charge of the system always remains the same, considering considering the system as a whole. So that is all about charge conservation. There is no excess or deficit of charge in any given system even after the electrostatic or probably electrical interaction between the objects involved. See, if we are considering the universe as a whole, what I'm trying to say is that the universe may be neutral, may be positively charged, may be negatively charged. We do not know. No one has gone out to the extent of the ends of the universe and found out how much exactly charge each body has. But what we know from this conservation of charge is that, be it positive, be it negative, be it neutral, the charge always remains conserved. That is, if it is positively charged by some value, that value will remain till eternity. There may be exchange of charge between particles that make up the universe. Similarly, any given small space, we bring ourselves back to any given small space where the interaction is probably between two objects, just like the example that I showed you. So in that case, the total charge remains the same even after they have interacted or exchanged charges amongst themselves. Now, having learned about quantization and having learned about the conservation of charge, what we can say is that the charge remains conserved. That means the total charge before any kind of interaction is equal to the total charge after that interaction. So we can try a few examples related to this case. So in the first case, we consider two objects, just like we did in the previous demonstration. So we have an object over here and another object over here, and they interacted with one another electrically, and there was some transfer of charge. So initially let them have charges of, say, 20 coulomb, and this one probably has more electrons, so this is probably having minus 10 coulomb of charge, and they were set to exchange charges in some way or the other until and unless they achieved some kind of equilibrium. Now, equilibrium means they will have the same amount of charge at the end. So this will have a charge q at the end, and this will have a charge q at the end of that interaction. So we wish to determine how much is that value q, that is the charge possessed by each of them at equilibrium, and what was the amount of charge transferred and who was responsible to transfer those charges. We'll also take a look at that. Now, just go by the by analytical method. What you observe is that, as I said, that electrons are always free to move about from one object to other, because they are not really tightly bound to the atom, especially the external electrons, the outermost electrons. So they are available for conduction, or they are available for to be transferred from one body to another body upon friction or upon conduction as well. Now, so the electrons, as we know, possess the negative charge. So that means that negatively charged body has an excess of electron, and this is excess of electron, and this body has a deficit of electron, and it is those electrons which will flow from the excess to the lower, or that which is having the deficit, in order to balance the situation. So what we get is, if we take that complete -10 out of that and place it in that +20, what we get is, from that -10 going out, this is left with a charge 0, and now this is left with a charge 20 minus 10 coulomb. So it now has 10 coulomb of positive charge, still positive, because there was a transfer of 10 coulomb of negative charge. Now, if we go by the case of transfer of electrons, there are still excess of electron in this 0 coulomb, and there is still deficit of electron in this 10 coulomb, because 10 coulomb is more positive than 0 coulomb. So that means still there is some interaction to be done in order to get the balance right. And what possibly could it be? Well, the possibility is that if it loses 5 coulomb of negative charge, because -5 and +5 would have been 0, so it loses 5 coulomb of negative charge, so now it becomes positively charged by 5 coulomb. And over here there was 10 coulomb of charge and -5 coulomb added to it, so it now has a charge of 5 coulomb. So now both those bodies have achieved equilibrium, that is 5 coulomb each, and there won't be any further interaction necessary until unless some forced interaction is taking place. We have achieved the total, the net charge, the final charge, to be the same. This is usually the case of conduction between two bodies, two conducting materials, or if we provide any conducting medium, it goes on conducting until and unless some equilibrium is achieved. We'll study that. We'll study about that in case of the methods of charging an object. So now we will discuss the formula that we can come up with. Well, the formula that we can come up with is that the charge possessed by the bodies in equilibrium, which is Q in this case, and that was obtained to be 5 coulomb, that can be obtained in a much more efficient manner with the formula that Q is equal to Q1 plus Q2 over 2. Q1 is the charge possessed by the first body, let's say, and Q2 is the charge possessed by the second body. And so we have 20 coulomb plus minus of 10 coulomb divided by 2, and so that gives me 20 minus 10 is 5. 20 minus 10 is 10 over 2 is 5 coulomb. So that's 5 coulomb, exactly the case that we obtained over here. And then if we wish to obtain the amount of charge transferred, let's calculate that first hand. Here we transferred 10 coulomb of charge, negative obviously, and here we transferred minus 5 coulomb of charge. So in all we transferred minus 15 coulomb of charge. So charge transferred can be given by this formula, that is, if we have, say, minus 10 was the excess of electron case, so minus 10 coulomb, so this is Q2 minus Q1 divided by 2, and Q2 in this case is minus 10, minus Q1 is obviously plus 20, so minus of plus 20 is minus 20 divided by 2, so that gives me minus 30 coulomb over 2, that is equal to minus 15 coulomb. So this was the amount of charge transferred. We also know about the case of quantization, because we know that minus 1 coulomb corresponds to 6.25 times of 10 raised to the power 18 electrons. We can say that for minus 15 coulomb of charge to be transferred, we'll have 15 times of 6.25 10 raised to the power 18 number of electrons were transferred from the second body that was having excess of electron to the first body which was having deficit of electron. You can calculate this out. This roughly comes out to, well, 90, and this is 25 times of 15 is probably 375. Is it 25 times of, yes, 375, 75, and 3 goes up, so 15 times of 6 is 93 times of 10 raised to the power 18 number of electrons were transferred. In a better way of writing it, we have 9.375 times of 10 raised to the power 19 number of electrons which were transferred. Now, the third property that comes in line is that of the invariance of charge. Charge does not change its value. Well, first of all, we need to understand how this question arises that any given charge may change its value. As discussed in the first video, charge is an intrinsic property of a given object. So is the case of mass. The mass is also an intrinsic property of a given object. But mass varies. Mass varies when we consider the relativistic motion, that is velocity in comparison to the speed of light, and it is given by the relation that m is equal to m naught over 1 minus v squared over c squared under root. Now this m0 is what we call as the rest mass, the mass that we usually observe for a given object, and this is the relativistic mass, which is obviously greater than m naught when v is nearly comparable to the speed of light. Nearly comparable, even the case of probably 10 raised to the speed of light is 10 raised to the power 8 is of that order, and if we have velocities nearly 10 raised to the power 6 at least for a given object, that can be considered as comparable, and that will definitely make some changes in the mass. So when we have those kind of relativistic speed achieved by particles, usually they are smaller particles like electrons and many other particles which are accelerated, then their masses do change. So there is no invariance when it comes to the mass of an object, but as far as the charge is concerned, it remains invariant every time. There is no relativistic case which can, increase the charge or decrease the charge of a given object. It is completely intrinsic. It does not change at all. So that is the case of invariance of charge. Not real mathematical case, but it's a theoretical one. The mathematics comes when we consider the case of mass given by the relation that I have written. Next, we consider the case of charge transfer, or even the case of methods of charging. Now they are usually by friction, as we have discussed earlier, by conduction, just in the previous example, and also induction. Now in case of friction, obviously the case of friction and conduction involve the contact between two objects which are to be charged. One may be previously charged, and that is going to influence or charge up the other body. In case of friction, however, you can have two neutral objects which will just which we just rub against one another, and the electrons of one of that object that gets deposited on the other, and the party losing the electron gets positively charged, while the one that receives those electrons get negatively charged. So friction, as we know, uh, the rubbing against of two objects, probably dry objects are much more effectively do get charged, and that is why in winters, mostly the dry season, dry climate, you have the clothes sticking to your body, or that is because of friction. They have, as you move, they have rubbed against your body, dry everything dry, the body as well as the woolen cloths probably, and as a result of that, when you take them out, you hear the crackling sound, because the attractive force, the opposite attractive force, has it breaks simultaneously, and as a result of that you hear those crackling sounds. So friction, we have discussed a few objects as examples, like the case of glass and silk, which in which glass obtains the positive charge and silk obtains the negative charge. We also have the case of ebonite and wool, or ebonite and uh, yeah, we can take wool. Wool here takes up the negative charge, and ebonite takes the positive charge, while the case of amber and cat skin or cat fur takes up the positive charge, and amber takes up the negative charge. Usually it's the solid objects that take up the negative charge, and the softer objects that take up the positive charge in these cases. But just the opposite is what we observe in glass and silk. Glass, being the solid one, takes up the positive in this case, and silk takes up the negative charge. So that's an exception, but usually it's the solid objects which take up the positive negative charge, and the softer objects, like the wool and the cat fur, they take up the positive charge. And that is why friction. Then comes the case of conduction. Now, in conduction, there is mutual contact by a conducting material, or probably between two conductors. So if we have supposedly a conducting material connected to two objects, and one of them is supposedly, say, charged and the other is probably neutral. Let's take the case that we are charging this object. Because this is neutral and supposedly this is a conducting material, then what happens is that it has those free electrons which can flow easily, and as a result of that, because there is deficit of electron, what will it do? It will try to move those electrons here to make it neutral, or at least to achieve that equilibrium. In case of conduction, the aim is always to achieve that equilibrium, that is, to obtain to level up the charges in both those objects. So it will keep on transferring the electrons right up to the point where this and the previous body, the neutral body, both of them have equal amount of charge. The other way around, if we are considering a body having negative charge and that is connected to a neutral conducting material, then the excess of electron over here, that gets transferred to the neutral object, and again, till the point the equilibrium is achieved, that is, both the bodies have achieved the same amount of charge in them, the conduction continues. And even if it's for a brief moment, it does the job. Now that's the case of conduction for you. In friction and in conduction, we involve the contact between objects, but in case of induction, there is no contact between objects. There need not be any contact. It is just the influence of one object over the other. One has to be the charged object, the other has to be probably uncharged or maybe conducting material having free electrons. So in that case, when one of the objects, suppose a stick, this is the case of induction, suppose a positively charged stick that is brought closer to a conducting material. Even in the case of non-conducting material, that's okay, because this charge will be strong enough or just strong enough to attract the negative ions or the negative charges present in that material to one side. It won't transfer, but it will attract those negative charges to one side while pushing the positive ions to the other side. So in that case, now this becomes partially negatively charged and this becomes partially positively charged. And that's usually the case. It's more proper in case of conducting materials which have abundant amount of free electrons. In case of non-conducting materials as well, you have a few charges to be collected at one end and the other type of charge to be deposited at the other end. At least the free electrons do get deposited to one side. So in that case, what happens is that that is when these opposite charges, unlike charges, they start attracting each other, which is why you have bits of paper sticking to a comb with which you would have brushed your dry hair. And that is exactly the case. That is the method of induction which has charged the comb. This is probably the comb which has got charged, and it is attracting the bits of paper which are obviously lighter, and they are getting attracted when this comb is brought very close to them. And you can also charge these things permanently. Take for the case of conducting materials, when you have a positively charged object brought close to a conducting material, suppose, and it is electrically neutral. So what happens in that case is that the electrons will be deposited to this side, with this being positive. Had this been negative, then the electrons would have drifted away to the other side, just like the positive charges that I am drawing in this case. So in that case, the electrons on one side and the positive ions on the other end, the partial charging has taken place. And now if we connect this to the ground, we earth this, then what happens is that the earthing provides or the earth, electrically neutral almost, it has abundant amount of ions available. At least the electrons are free to move, so it won't matter if a few electrons go out of earth, it will still be zero. So these electrons, they find that this is partially positively charged and they move towards it. Then they make it electrically neutral, this side, and then we can disconnect the earthing. And after disconnecting that, what we get is this body which was previously neutral and then it had become partially charged, now will acquire only the negative charge in excess, that is present in excess, that was not neutralized by any other positive ion. The positive ion on the other side was neutralized by the electrons that flowed from the earth, and then with the disconnection done and dusted, this body eventually acquired a permanent negative charge. And well, the charge is obviously conserved because here the system involves the positively charged body, the neutral conductor, and the earth. So the three taken together, the total charge obviously remains conserved. So there's no point of thinking that where did this negative charge in excess come from. Well, this negative charge was transferred from the earth. Earth lost some amount of negative charge, but that amount is highly negligible to make any effect to the net charge of the earth itself. So that's like taking a cup of water out of the sea. That doesn't really make any difference. And then in the same manner, by induction, you can also permanently provide a positive charge to any conducting material when you bring a negatively charged object to in its vicinity, and then you earth it. And in that case, it's the other way around. The excess of electron that are deposited on the other side, they are transferred towards the earth. Let me just draw that. So this is a negatively charged object which is brought closer to a neutral conducting material, and as a result of that the positive ions get deposited on one side and the electrons are pushed to the other end, which is then earthed. This partial charge, that those electrons being free, they get transferred to the earth. Again, the earth is just like adding a cup of water to the sea, so it doesn't really make any difference to the earth, but it does make a difference when we cancel out this earthing and disconnect that, and this body now consists of a net positive charge. So these are the methods that we employ to permanently charge a few objects by the method of induction. So these are the three methods on the whole about the transfer of charge as well as the methods of charging objects, that is by friction, by conduction, and by induction. So with this knowledge available to us, let's try an example and see what we have learned. I'm using the space over here. So let's say we have three objects, A, B, and C. This is an example. Now A, B, and C, they are identical spheres probably, and they carry charges, let's say 6 coulomb, 4 coulomb, and 2 coulomb. Now it happens in this case that first body B and A are contacted or made to touch each other for a few moments. They are conducting materials, of course, so there will be transfer of charge, and then they are separated. I'm not writing the question in words, I'm using symbols so that it's easy and quick. Then they are separated, so A and B are separated now. They will carry some charge, we do not know what. Now body B is contacted or made to transfer some charge probably with the body C. So here was the conduction between A and B, and here there is the process of conduction between B and C, and that's for a little interval of time, small interval of time, and then they are separated as well. So C will carry some charge, B will now carry some charge, and A already carries this amount of charge. Let's see that this is suppose Q1, this is Q1 dash, and this one was something with C was having 2 coulomb. So finally you have Q1, all that remains with A, you have Q2 now remaining with B, and some charge Q3 remaining with C. Let's see what is that value of Q1, Q2, and Q3. That is the question. So in this case, we go back to the first instance where A and B were made to contact one another and there was conduction involved, and in that case you have the net charge after transfer Q1 is equal to Q1 primed, and that has to be equal to 6 plus 4 over 2, that is 5 coulomb each. That is as per the formula that we have discussed in the previous page, that is this one, that is q1 plus q2 over 2. That's the total charge after possessed by each of those bodies in equilibrium. So they will be achieving some equilibrium, and in equilibrium they will be having this amount of charge. So we now have the permanent value of q1, which was to be determined. What about q2? Well, q1 primed being equal to 5, it was in contact with that body C for some amount of time, some interval of time. So 5 coulomb and then plus 2 coulomb, which is that carried by C, divided by 2 is what we have the final value of q2 as well as q3, because q2 will be equal to q3 because they were the last pair to conduct charges and be in equilibrium. So this is now equal to, well, this is 3.5 because that's 7 over 2. So this is 3.5 coulomb of charge. So we can add one more question to that. This is fairly easy. The question that I would like to add to this is that who transferred how many electrons? So that's another question that I've added to this. Now the question of transfer of electron, it's quite easy to see which one had the least amount of charge, least amount of positive charge. The least positive will have more electrons. So body C has the least amount of charge, but in that first interaction between A and B, in this case, body B had 1 coulomb less than body A, that is positive charge. So obviously it has transferred 1 coulomb of electron, that is minus 1 C, to A, and as a result of that it has gained a charge of 5 coulomb, while B also gained a charge of 5 coulomb by losing minus 1 coulomb. So in the first case, B transferred minus 1 coulomb of charge. Minus 1 coulomb corresponds to 6.25 times of 10 raised to the power 18 electrons. This was in the first interaction. Now in the second interaction between B and C, C consisted of the least amount of charge, and the final charge was 1.5 coulomb greater than what C had possessed. So that means in the second case, C transferred, you can use the formula q2 minus q1 divided by 2. That's what I've given you in this previous segment, charge transferred q2 minus q1 over 2. You can use that, but it's pretty straightforward when we see who has lost and who has gained. So C transferred minus 1.5 coulomb of charge, and as a result of that B gained minus 1.5 coulomb with that 5 coulomb it had, and so final charge for each of those bodies was 3.5. So minus 1.5 is 3.5 times greater than this, so this is 3 by 2 times of 6.25 times of 10 raised to the power 18 number of electrons. That's the case over here. So this is how we obtain the case of how many electrons are transferred and what amount of charge is possessed, or how much charge was transferred in the first place as well. So that's all from this video. We'll be dealing with the case of electrostatic forces and some more questions related to the topic in the upcoming video. Till then, thank you for watching.